Good morning, everybody. So one thing I forgot to mention, although I think it was probably kind of obvious, is that the homework, I released the homework at the beginning of class, but obviously we hadn't covered all the problems at the time it was released. But by the end of this week, every problem will be covered. So the second to last problem is on templates, which will be covered today. I mean, the general knowledge will be covered. And then with edge detection on Thursday, you'll be able to do the last problem. So generally, I give you at least 2 weeks to do the problems of the homework. Sometimes I might release the homework and expect that you won't get to the last problem until a couple days later anyway. So I might release the last homework I might release the homework even though I'm going to teach that subject in like 2 days. But all right, so just brief review. So we've talked about so far filtering in the spatial domain. So this is when you slide some template or some little matrix over the image and compute the product of corresponding elements with the local image patch, and then store the result at the center of where the patch is over the image. You can also look at filtering in the frequency domain, which is when you convert the image and the filter to a frequency image, an FFT. And then in the frequency domain, convolution is multiplication. So you just take the element-wise multiplication of the FFT of the real image. Here, only the magnitude is shown, but you actually do the element-wise multiplication of the imaginary numbers of the FFT. So it'll be the phase and the magnitude. With the FFT of the filter, that gives you your filtered image in the frequency domain, and then you do the inverse FFT to get the original. So sometimes it's easier to think about a filter in the spatial domain. Sometimes it's easier to think of its behavior in the frequency domain. So it's just a review of viewing these frequency domain images. A couple of things to note about this plot. One is that it's displayed using FFT shift. If you just try to display the result of an FFT directly, it will put this 0 value in each of the corners, and it's kind of hard to interpret. FFT shift puts the 0 in the center. It's also displaying the log magnitude, and this color bar, in case you haven't seen a pseudo color plot, the colors represent a number that could be outside of the normal RGB range, and then this bar here shows you what the number is. Also, you can use the figure tools to click on particular pixels and see the values. So in the FFT plots, the orientation away from the center gives you the orientation of the frequency. So for example, horizontal edges would be a strong vertical frequency. So you might see some power up here from a lot of horizontal edges. These are diagonal edges that go in this direction, like the floorboards or the edges of this window. And then low frequencies are, the higher the frequency, the more it is towards the extremities of the plot. So a super high frequency will be out in the exterior. Low frequency is on the interior. So today we're going to talk about a lot of applications of filtering. Template matching, a very basic form of pattern matching. Image pyramids, multi-scale representation of images. Filter banks and texture. It's a way to how we can start to represent the statistics of regions and characteristics of regions rather than just looking at responses of single filters. And then a little bit about denoising and how compression works for JPEG and PNG. So let's start with template matching. So our goal here is we have some patch, that's our template, that we want to find in an image. So the main challenge in template matching is that you have to define some kind of similarity measure. So what makes this patch similar to some other patch in the image? Intuitively, if we're looking for eyes and this is our template, we'd be like, okay, we want a strong response on each of Einstein's eyes, and we don't really want a strong response anywhere else. But then we have to mathematically define some kind of similarity measure that will have that property, that it will have a high or strong response at the eyes, and then a weak response everywhere else. So there's a lot of different kinds of similarities we could consider. We could just do correlation, zero mean correlation, sum squared difference, and normalized cross correlation, among many others. But these are the ones that we'll go through today. So here's method 0, because it's not a very good method. Filter the image with the eye patch. So I can just take this, and I do IM filter this image with that image, and I'll get a response. Does anybody have an idea what this response will look like? Yes? Right, yeah, it'll just be kind of a blurry image because so far this will have 0 values where it's black and 1 values where it's white and otherwise in between. And so basically you're just computing a weighted average of the local patches. And so it's just a weird kind of smoothing. So obviously that's not the kind of response that we want. So here's a very simple fix. The simplest fix you could think of, which is just to subtract the mean of the template before doing the filtering. So here we have the image filtered with the template. Here G is the template and F is the image. And this means that for every output pixel, we're taking the sum over the corresponding elements of the template with the elements of the filter, local to MN. The elements of the image local to MN. So if I just subtract the mean, now I get some better response. So the reason why this sort of works is that filtering with the mean subtracted template means that if the image is dark where this is dark, then it will not subtract, or let's say if the image is bright where this patch is dark, then it's going to have a strong negative value. If the image is bright where this is bright, then it's going to have a strong positive value. So at least you're sort of looking for bright patches that are surrounding dark patches. So here this is the filtered image, and it's scaled. So these are not 0 to 255 or 0 to 1 values. They're whatever the filter response is. Then it's rescaled, so high is white and low is dark. So if I threshold it, meaning I say that the response greater than some k any response greater than some k will be white, and any response less than some k will be dark, then I get this image. So here you can see that this is a very small dot, but it's actually there. So there's true detections that were where the response was high enough over the eye, and then there's a bunch of false detections where the response is high, like over the collar. And so the downside still of just doing this mean subtracted filter is that it's going to be more sensitive to areas of the image that have strong intensity or strong variations of intensity than areas where it has weaker intensity. So for example, if I filter a black part of the image with this patch, it's just going to have a 0 response. Well, actually, if I filter any uniform area, it's going to have a zero response. So that's not a good example. What happens here is that over the collar here, I get these really strong responses. And it's actually strong responses, I think, on this part of just above the collar. And that's because you have a really bright area on the outside and a fairly bright area on the cheek here and a dark area in the center. So that super bright collar really boosts up the response based on like the outside of the eye here. And it even gives a higher response possibly than the eye that I drew the template from. So what's a better idea? So far, basically, the mean subtracted filter says, I want the image to be bright where my template is bright and dark where my template is dark. But the downside is that if the image is like super bright where the template is bright, it will be even better than if it had the same brightness. So what's the kind of straightforward way to address this issue? It was simultaneous, but OK, we'll go with you. Yep.
Sum of squared differences?
Right, so sum of squared differences. So basically, you just say, and this is probably those other two things that I said are not the first thing somebody would think of. Usually, this would be the first thing somebody would think of trying. So sum of squared differences means that you want every pixel value to be close, every pixel value in the local image patch to be close to the pixel value of the template. So it's really not good if the color is brighter than this area of the eye. You want it to be the same color as that area of the eye. So here, so the way that sum of squared difference works is that you move this template over the image at every position, and then at every position you take the difference between the corresponding elements of the template and the local image patch, square that difference, and then take the sum. So sum of squared difference is a pretty literal title for that method. So if you do one, this is here showing 1 minus the sum of squared difference. So sum of squared difference is that if the value is low, it means that you have a good match. And if the value is high, it means that you have a bad match. So I'm showing 1 minus the square of sum of squared difference, and then thresholding it. And now we get true detections. We don't get any false detections. So, so one possible downside you might spot is that sum of squared differences looks more complicated. It doesn't really look like a linear filter. It's a quadratic function. So do you think that, can this be implemented with a linear filter or with a set of linear filters? So it's a somewhat hard question to answer quickly. So let me tell you that it can, and instead think about how, why can it be implemented with a set of linear filters? Yes?
Does it have something to do with expanding the square?
Yeah, exactly. Yeah, it definitely has something to do with expanding the square. So, so let's do that. Actually, let's grab a pen. And let's see how this works today. Okay. Ooh. I wonder if it helps if it has like, it's kind of like those eye tests. Okay, I figured it out. All right, so we're doing sum of square difference. So basically, you have the sum over some ij of your template with your image patch squared. So if we just take that, oh man, it's going to try to refigure out. And if it does that every time I write. Okay, so if we just expand this, then we have the sum over ij of gij squared minus 2 gij times f m plus I n plus j plus f m plus I n plus j squared, right? And I've got that, so for every local image patch, I compute that summation, and then I store that response at the center of the local patch. So let's do the first one. So sum of Gij, this is the template, the sum of the values of the template. So that's not really a filtering operation, but it's pretty simple to do. So that's just going to be sum of G, sum of G squared. So I did sum of all the elements of G using MATLAB notation squared. Now, this part here, so how do I implement that using a filtering operation? So I'm taking the sum of the product of corresponding elements of the filter with the local image pixels. So that should sound familiar, right? Minus 2 times that. So what is that in terms of image filtering? Yes?
Filter of G.
Right, so it's just, yeah, I just have to do minus 2 times, it's just an image filter, basically. And then I've got a minus 2 there, so I can do minus 2 m filter, I'll filter f with G. And then the last one is the trickiest one. So I want to sum the squared elements of f over the local patch. So sum the squared elements over the local image patch. So how do I do that with the image filtering operation? Yes?
Image filter FF.
Image filter FF with F with itself?
Yeah.
No, you're thinking in the right direction, but that won't do quite what we want, because that will actually filter the entire image with the entire image. So you'll end up with something that looks really blurry. That's called autocorrelation. So you would get the, you'll get the sum of squared values of the entire image at the center of that resulting image. But you really want the sum of squared values of each local patch at the center of each local patch. Yes? Right, exactly. So the answer given was first square all the elements of the image, and then filter that with all ones of the size of the template. So I can do hoiem filter f squared with ones size G. So one size G just creates a ones patch that's the same size as the template. And so that will sum over the domain of the template for each local patch. And so I'm summing the squared values of f. So this is SSD using linear filters. So SSD is actually a pretty efficient kind of template matching to do as well. Almost as efficient as mean squared filtering. But you just need to do 2 filters instead of 1 filter. And if you have a really large template, then you can do it using Fourier transform. So let's switch back. I'll have to figure out eventually if there's a way to tell it that it's got the right focus and stop moving. Okay, so now imagine that I use SSD, and Einstein decides to wear some virtual sunglasses so that he's not detectable, or his eyes are not detectable. So what's going to happen now? Is this going to provide a good detection, or is it going to mess up the template? The template matching. So how many people think this will work well? How many people think it will not work well? Okay, most people, unanimous out of those who have voted. So yeah, so this is what happens if I do the filtering now. You get these horrible responses over the eyes because actually all the values here are far from all the values there. So, so that totally failed. So the downside of template matching is that if your overall intensity of the image changes, then it's going to really mess up your template match. So if, for example, you took a picture of a scene and then the lighting changed, then you took another picture and you tried to use a template from one image to do matching in the second image, it wouldn't work. It might not, well, it likely wouldn't work very well because the overall intensity of the second image may be different than the overall intensity of the first image. So that's where normalized cross-correlation comes in. So normalized cross-correlation wants to kind of get rid of all the annoying factors that might vary from image to image. So one thing is that you subtract the mean from the template. So you're doing mean subtracted filtering, sort of. Then you also subtract the mean from the image patch. So that makes it that if you have any image and you add k to it, then it's not going to affect the response. But what if you have an image and multiply it by k? That would still affect this numerator here. So we have the denominator as well. So in the denominator, you divide by the standard deviation of the mean subtracted filter with the mean subtracted image patch. So if we multiply f by k now, and you work through all this stuff, you'll get k squared here, we're multiplying f by k. So you'll get k squared here, and so you'll get k outside of this sum, and then you get k times f, k times mean of f, so k outside of that sum, so the k's cancel out. So what normalized cross-correlation does is that if you scale the image by multiplying it by any k, or you shift the image intensities by multiplying it by by adding any n, then the response will not change. So it's invariant to shifts of intensities and to scalings of intensity. So that means that it's going to be pretty robust to changes of the gain of the camera or changes of lighting. So if we repeat this experiment, so for normalized cross-correlation, on the original input image, we get this response. Now here, for normalized cross-correlation, you want a strong response. That means a good match. So it works for this case. And then also, when we put on the sunglasses, there's not a big change. The only change, in fact, if I flip between these, there's some change to the overall range, which is why it's getting darker. But it's the same pattern, except like right on the edges of the sunglasses, where there's been some relative change in different parts of the window. So the response, and then if I threshold it, I get exactly the same detections that I had before. So normalized cross-correlation is a better method if you expect that there might be a significant change of overall intensity between the image that you'll be doing the detection in and your template. Question?
So when you move the mean, you take the mean of the whole image?
No, that's a good question. So you move the mean of just that local patch. And so for that reason, this is not, so actually this is not something that you can implement with linear filters. So there's, yes, question?
What if the glasses are only covered like half of one eye?
If what?
If the glasses are like covering half of an eye?
Oh, yeah. So the question is, what if the glasses just covered half an eye? And it would still work in this case, as long as where it would create a problem is if you like striated the glasses, or meaning like you broke them into strips, or if like, as long as this whole patch where you want the detection to occur has changed in the same way, then you'll be fine. But if you add a bunch of edges and like changes of intensity in that area, then it could throw off the filter. Yeah, so this part is not something that you can really do with a linear filter. So we talked about a few different methods. Usually the answer of what one to use depends, because you usually have to trade off computation with accuracy, and it depends on the situation you're in. So the zero mean filter is the fastest, but it's not a great matcher. But it's still something that you might use if your purpose is not to really do end detection with your template, but you just want to generate features, then a zero mean filter makes a lot of sense. Sum of squared difference is also pretty fast, and it's sensitive to overall intensity. That can be a good thing or a bad thing. So if you're doing tracking or stereo, then sum of squared difference can be a good similarity measure. So in tracking, you're trying to find, over successive frames, you want to rematch some template of the object or some feature. And it kind of makes sense to use SSD because you would assume that there's not going to be much change in lighting between successive frames, and you can hold the gain of the camera constant. Likewise, for stereo matching, which is when you find corresponding patches across two images, they're taking the pictures, if they're taking pictures at the same time, and it's the same camera, or like another copy of the camera, then SSD makes sense because the lighting is constant, the camera gains can be held constant, and so you would expect that there'd be an exact match. Normalized cross-correlation is slower than SSD, but it has these extra invariances. So normalized cross-correlation might make more sense in a situation where you're trying to match across images taken at different times or by different cameras. So for example, in multi-view stereo, where you might have several people taking different pictures of a scene, and then you want to try to extract depth from that, you might use normalized cross-correlation, assuming that they might be taking pictures at different times of day. Also, normalized cross-correlation might be used for, like, if you're detecting, if you had like a stop sign as your template and you wanted to detect other stop signs in other images. Question?
So if you're using like a bag of words method for like feature detection, which of the methods would you mostly use?
So the question is, if you're using a bag of words method for feature detection, right? Yeah. Which of these methods would you use? So let me see. So I guess bag of words is a different kind of thing. So let me take a step back. So the way that like bag of words works, if you're trying to do like detection, for example, or if you're trying to get interest points for matching, is that you first detect some stable locations in an image, and that you could see that will be done neither with neither of these. It's sort of like a corner matcher usually, or something like that. Then you take the patches from these images and you assign them to clusters based on other data that you've extracted. And then you can, based on the cluster that it falls into, then you can do matching for recognition or for like structure for motion or something else. So I guess it's really, it has some similarities to SSD in that when you're assigning a patch to a cluster, you would often take the difference between the sum of squared difference to each of the cluster centers and then assign it to the nearest cluster center. But it's not exactly doing any of these. It's a bit more complicated. So, so far I've just done fixed size template matching. So I had a template of the right size, and I didn't try to find smaller or bigger eyes. So there's an easy way to deal with this, which is that we create what's called an image pyramid. So remember, we talked about sampling in the last class. And if you want to sample, meaning if you want to get a downsample, for example, get a smaller image, then you first run a Gaussian filter that kills off the high frequencies that would otherwise cause aliasing. Aliasing means that you introduce frequencies that weren't in the original image by undersampling it. So we run the Gaussian filter, we get our low-pass filtered image, smoother image. Then we sample every other pixel, and then we get a low-resolution image as a result. So we can just do that repeatedly. So we start with an image that's 512 by 512, smooth it, downsample it, smooth it, downsample it, smooth it, sample. And so we create this whole pyramid. Here they're all resized to be the same size, but here they're shown in the true resolution. And so you get a multi-scale representation of the image. Now, if you wanted to detect something in this image, like a zebra eye or something, even though there isn't one here, then you can just run that fixed size template in each of these different images, and the size of the template will be larger relative to the smaller images. So here you'll be detecting small eyes, and then bigger eyes, and bigger eyes, and bigger eyes, and then down here it'll be like the whole image would have to be an eye to have a match. So to do template matching with pyramids, you match the template at the current scale. Sometimes even you would upsample the image so that you can detect something that's smaller than the template. And then you downsample the image, so you blur it and subsample. In practice, you don't usually want to go by a factor of 2 because that will be too large of a scale step to do accurate template matching. So you would, in practice, usually do a scale step of 1.1 and 1.2, or between 1.1 and 1.2. And then you repeat until the image is very small. So you just keep on downsampling and then running your filter, and downsampling and running your filter, and downsampling and running your filter. At the end of this process, you'll get, you can take all the responses that are above some threshold, and then optionally you can say that if neighboring responses are both strong, then you only keep the stronger one. Because typically, if you have a very strong response at some pixel, you'll have some weaker response at surrounding pixels. So this, if we're doing SSD, would be a very simple detector. But even if you're doing more complicated detection methods, it basically, many of the more complicated detection methods work very similarly. It's just that they have much more complicated filters that they're using to produce the scores. So another kind of pyramid that's very important is a Laplacian pyramid. So the Laplacian filter can be approximated as a unit impulse minus a Gaussian filter. So in other words, it just keeps all the frequencies that the Gaussian filter discards. So you can implement it as just you filter an image with a Gaussian and then subtract the filtered image from the original image. So we can also create a Laplacian image. And this is an idea that came from Burt and Adelson in 1983. So you get the highest resolution image corresponds to the highest frequencies, and then each lower resolution image corresponds to lower and lower frequencies. So I'll have an illustration on the next slide for how to compute this. So this gives you a multi-scale representation where you're kind of representing the different frequencies and the different scales. So now this is like the super edgy parts, and then this is like moderate edgy parts. So you can see that the strong responses here are at like the little hairs on the zebra, and the strong responses here are at the edges of the stripes of the zebra. One reason that this was one thing that you can use this for is as a kind of compression. So you can, this image is very highly compressible, while these images are less compressible, but they're smaller. And then there's a bunch of this is also used to do blending of images, where you can take two images, do this pyramid to both images, and then quickly blend among the higher frequencies and more slowly blend among the lower frequencies. All right, so this is how we create we can create a Gaussian and Laplacian pyramid at the same time. So here I'm doing it with a hybrid image. We've got the initial image. That's the top of our Gaussian pyramid. I downsample, I smooth and downsample. So I smooth G1 and then downsample it to get G2. Downsampling means that you take every other pixel. So it's like m 1 colon 2 colon end, comma 1 colon 2 comma end print. I subtract the okay, so I subtract the this is a slightly better way to do it than just subtracting the smoothed image. So then I upsample G2, so it's back to the original size as G1, and then subtract that result from G1. Or if I want to do a quicker approximation, I can just take the smoothed image and subtract it from the original, and then I get L1. So L1 contains everything that G2 has lost, right? If I upsample G2 and add it to L1, then I get back the original image. Then I downsample, I take G2, I smooth it and downsample it to get G3, the lower resolution. Then if I take G3 and upsample it and smooth it, then I get back and subtract that result from G2, then I get L2. And then I can keep going. So, question? So upsample means that for you generate more samples than you had originally. So one way of doing it is that you take every pixel and copy it 4 times so that every pixel becomes a 2 by 2 block. So that's what we would do in this case, upsampling by a factor of 2. Question?
How do we downsample with a factor that's not 2, like 1.1%?
So you can sample an image at a floating point value, but you just need to interpolate. So typically you would do it with some kind of bilinear or bicubic interpolation, which means that you take the surrounding values and then you take some kind of average or combination of those values to estimate the value of the pixel at that floating point position. Okay, so so this says, so you use the same filter for smoothing in each step. So you would use, for example, a Gaussian with a sigma of 2. You typically want it to have a cutoff frequency that's about 1/2, so that you are removing the frequencies that will not be representable in G2. And then you downsample or upsample using you can downsample or upsample using nearest interpolation, which means for downsampling, that means that you just take the nearest pixel. In the case of downsampling by a factor of 2, you land right on each pixel. And upsampling with nearest interpolation means, like I said before, that you take each pixel and you copy it into a 2 by 2 block of pixels. So you end up with an image that's twice as big in each dimension. So, so here, this is showing on the top we can see the Gaussian pyramid, or no, that's not right. On the top we see the Laplacian pyramid, and on the bottom we can see the Gaussian pyramid. So the Laplacian pyramid, this is the very high frequencies, and because this image was created by blending the high frequencies of a cat with the low frequencies of a face, human face, then we get in the high parts of the Laplacian pyramid, it's almost all cat that's represented. And then as we get into the lower frequencies, then it becomes more the face that's represented. So as you go lower, as you get into the smaller parts of the Laplacian pyramid, it's representing the lower frequencies. And then if I look at the Gaussian filters, originally we have high resolution, so it's like the original hybrid image. And then as we get into lower resolutions, I'm basically representing the lower frequencies, so it looks like the face. So we can also reconstruct the original image from the Laplacian image. So to do that, so here we have our Laplacian pyramid. So the little guy, and then the bigger and bigger ones until we get to the highest resolution part of it. So to reconstruct the original image, we just upsample the last level of the pyramid and then smooth it with the same smoothing filter we used before, and then add it to the next level of the Laplacian pyramid. So that will give me G3. It'll give me G3 exactly, since the way that I created L3 was by upsampling L4 and subtracting it from G3. Right? Question?
So for the parameters of the smoothing, Gaussian smooth, should it be the same for every level, or must it change as the level comes small?
It should be, the parameters should be the same for every level. And the reason, well, typically it should be the same. And the reason is that you're always, so when you apply like the same Gaussian to a smaller image, it's actually like a higher Gaussian, like in terms of the width of that image. So it covers like a larger extent of that image. And so the effect is that you keep on focusing on lower and lower frequencies as you go down. Question?
What do you mean by adding L3 to the smoothing?
Okay, so the question is, what do I mean by adding L3 to the smoothed up sample? That's a good question. So it just means that you element-wise add the values of the two images. So after I upsample L4, it will be the same size as L3, but it will be blocky. So every pixel in L4 will be a 2x2 block of the same value. And then I smooth it. And then I add each element of that upsample smoothed image to each corresponding element of L3. So in MATLAB, it would just be, like if I want to add images I and j, it's just I plus j. And that adds each of the corresponding elements. Question in back there?
When you upsample, is there any specific rule that we have to have the two pixels, for example, on the right side or left side or which direction?
When we sorry, can you say that again? When we upsample, do they have to be?
Well, if I understood you correctly, you said that you take each pixel and then make a copy of that and then put them together. So when you want to put the second pixel, is there any specific rule to say it should always go to the right side or left side or anything like that? Because if it's not, then it's not guaranteed that they always go to the same, like G3. We can put it on the other direction.
Okay, so the question is, when you upsample, do you, so if you think about like, let me take like a little, oh, this isn't, you're not going to see that. Okay, I'm going to have to switch and then it's going to freak out, but let's do it. So let's upsample this little image. So you could think about like that. I've got some values here from the original, and then I guess I made those too small. But anyway, so the question is, I guess, like, would you? Sorry, this is getting messy. Okay. So I think the question is, like, do I think about it as putting this in the upper left corner and then, like, filling in the values to the right and below? Or do I think of it as, like, putting in this value in the right corner and then filling in the other values? But really, no matter how I do it, I'm going to end up with the first 2x2 pixels are going to correspond to the upper left pixel. And then the next 2x2 pixels will correspond to the next pixel. And so regardless of how I implement it in terms of like which pixels I fill in first or whether I think of it as like extrapolating to the left or extrapolating to the right, at the end of the day, I'm going to have the same image. So either way, I'm going to end up with an image that looks like this, where every original pixel has like a 2x2 block. And then I'll define this now as my first pixel. Question?
While upsampling, would it be a better idea to take the mean of neighboring pixels and then
And so I think the question is, so I think you're asking for upsampling. Would it be better to take the, I think, let me restate it and see if this is accurate. So I think you're asking, like, why do this, like, nearest upsampling where I just copy a pixel rather than, for example, I could say that this value here should be 1.5 or something close, just under 1.5, since it's sort of in between the 1 and the 2. That would be typically, if you do upsampling for the purpose of making a larger image, you would want to do that interpolation. In this case, the smoothing does the interpolation for us. So after we upsample and then smooth, it's kind of an equivalent thing. Also, the way that this was designed, since if you do some kind of like bicubic or possibly even bilinear interpolation, you might not, the downsampling and the upsampling might not, the downsampling and upsampling might not exactly recover the same information. But the way that this is defined, because I have this like very simple upsampling and smoothing, and I can easily parameterize that and do it the same way every time. And then I know that when I add this to L3, then I'll get G3, because L3 was created using the difference. But I think there's nothing, if you implement it as doing bilinear interpolation, which I think I've done before, you'll get some small loss usually in the reconstruction at the end, but it will be really small. So I just keep doing that. And at the end of the day, I get back my original image. And so let me just delete this. I actually had, at the start of the day, this said lossless. And then I was like, wait a minute, it's not actually lossless, but it is. OK, so you use the same filter for smoothing as you use for deconstruction. And you upsample with nearest interpolation. And as long as you do that, follow all those directions, then the reconstruction will be exactly lossless. You'll get back exactly your original image to floating point precision. OK, so image pyramids are actually used for a lot of stuff. We can use it for compression, as I'll describe a bit later. We can use it for object detection, which is like a fancier form of template matching. We can use it to detect features. We can use it to detect stable interest points, something that we'll cover later in the class as well, in the semester, I mean. And also for registration, which means trying to align two images. So for registration, we can do course-defined registration. And that application we'll cover right now. So I'm going to cover it kind of at a high level because I want to get to some other things as well. But so imagine that you've got two images and you want to line them up. So you think that they're images of the same scene taken from similar positions. For example, if you took took a picture out your door before it snowed, and then it snowed a lot, and then you took another picture. So it's like almost the same exact picture, but not exactly aligned, and you want to line them up so you can do a crossfade. So here, in that case, we might say, well, we're just going to try to translate one image until it aligns with the other image. If you're doing that at full resolution, it's kind of slow. If you had two 8-megapixel images, that means that you have to translate one image over the other. And if you did if you searched the full space, then the computational complexity would be number of pixels squared, which is 8 million times 8 million, pretty big. So there's a technique called course-defined image registration. And this is used both to align whole images and also to align smaller image patches, like if you're doing tracking, for example. So the idea is that you create two pyramids, one pyramid for each image. And so you end up with this multi-scale pyramid. And then you first do matching or registration at the coarse scale. So I think I will actually have to draw this. Otherwise, I think it's not going to make a lot of sense unless you already know what I'm saying. OK, so I create two pyramids. So this represents the small box is low resolution, the high box is the original image resolution. The naive registration would be that I take the image on the right, and then I just try every translation and match it to the image on the left, and then take the translation that has the lowest sum of squared difference. Instead, what I can do to speed things up dramatically is just first do the alignment of the low resolution images. So let's say that at this translation, the image on the right best matches the image on the left. So if I shift it by the center minus this, then that gives me some guess of how the higher resolution images will line up. So I can upsample that prediction. So I can say, in this image, I think that the best translation will be somewhere within this little window, some like 7 by 7 window, for example. And then I find the new best position based on the higher resolution images. And then I upsample that prediction. And then I search again a local window. So because the local window that I search is a fixed size, maybe 5 by 5, 7 by 7, that time is very small. It's just it's going to be the number of pixels times the size of the window. So it's going to be basically like O of n. And then because this is very small, then because the low resolution image is very small, then this matching is also very fast. And so in the limit, you could do this, and you turn an O of n squared operation to an O of n log n operation. So this kind of trick is used a lot in like matching for tracking or for stereo, any kind of patch matching. All right, so it's faster because, oops, switch back to my slide. Okay, so it's faster because I start with the matching at the course level, which is fast because the images are small. Then I use that to predict where in the higher resolution image the match should be, so I only have to search some local translation in the higher resolution image. And that stays true even as I go up to the finer and finer resolutions. So are we guaranteed to get the same result? So will this give me the same, am I guaranteed to get the same match that I would have gotten if I used high resolution images to do the matching without a pyramid? Great, so somebody said no, and that's correct. So I won't necessarily get the same result, and especially if the match depended on very fine details, then those details will be blurred out in the coarser levels. In practice, though, it can actually, in practice, it usually works pretty well because most images are largely smooth. So if you go down like 2 or 3 levels in your pyramid, typically this coarser image will still contain most of the useful information that was present in the original high resolution image. And in fact, it will have less noise. And so in practice, usually doing a course-defined registration with say, like 2 to 4 levels of your pyramid, depending on the original resolution, will produce good results. Sometimes it even produces better results than if you did a fine resolution to begin with, because you start with a less noisy image, albeit lower resolution. So we've talked about a few different image representations. There's pixels, which have really high spatial resolution, but you don't really get any access to frequency. You don't directly represent local changes. The Fourier transform represents how much power there is in different frequencies of changes, but you don't have any spatial information that's easily accessible. And then the compromise is pyramids or filter banks, the latter I'll get to in a moment, which balances between the spatial information and frequency information. So you can both see where the frequencies are, or how much power is in the frequencies and where that power comes from. So let's look at how we can represent texture using filter banks. So this is an image with lots of texture. You can think of texture as changes in the intensities that are due to small geometric or coloring or small changes in geometry or coloring of the surfaces. So it's like smooth here, it's more like speckled here, it's kind of a mix of speckled and linear over here, and so on. So you'll get changes in texture due to different materials. So the wood and carpet and fur all have very recognizable and different textures. You can get changes of texture due to changes of orientation of the material. So you can tell which way this bark is really facing. So if this is the trunk of a tree, then we can tell that this is like an upright picture, while these are probably not upright pictures. So the texture is going this way here and this way here. Also, texture can vary with scale. So because it can vary with orientation, scale, and material, it means that texture is also a clue or a cue that can be used to predict the scale, orientation, and material. So, like I said, one way to say what texture is that it's changes of intensity due to variations of local geometry, local surface geometry, or albedo. You can also think of it as regular stochastic patterns caused by bumps, grooves, and/or markings. So the question we want to address now is, how do we actually represent texture? And one nice way to do it, very simple, is that we compute the responses of blob and edge filters at different orientations and scales. So one example of a filter bank is this Long Malloc filter bank. And so this has a bunch of edge detectors. These are detecting big edges. These are small edges. So these are like fatter or lower frequency changes. These are high frequency changes. Different orientations. These are bars. So like if you want to detect like a nose would be like respond to a very wide bar, or pole or wires might respond to thinner bars. And then these are what I call blob filters, because they're looking for a dark area in the middle of a sea of white, or a bright area in the middle of a sea of black. And this is just overall intensity. It's just the smoother. So I can process the image with each filter and then keep the responses, or sometimes you only care about the squared responses or absolute responses. And then I get some characteristic of the texture by combining all of those responses across each pixel. So here you can see that this is the response of this finer blob filter, and it's responding on the little dots of the butterfly as well as some of the edges of the fronds. This is a coarser blob filter, so that's responding even more strongly on these bigger dots of the butterfly. This is a horizontal bar filter, and here's a diagonal bar filter, which responds really strongly along those, I guess I'm calling them fronds, I don't know if that's correct, but whatever these things are. And then you've got different oriented bar filters. So each one gives you a different response, and by combining them together, you get some idea of the overall texture. So then let's say that we want to do a texture, represent the texture of the whole patch. One way that we could do that would be to record some simple statistics like the mean and standard deviation of the values. So if you took, for example, the absolute responses and then you took the mean, then you would be saying like how much general little bumpiness is in this image and how much big bumpiness is in this image, how much diagonal bars are in this image. So that's what was done in this figure here. So we've got these 7 filters. So this is big blob and different oriented edges. And I've got these 3 images that I applied it to. And then I took the mean absolute response. So white means that there's a strong response. So this means that there was a strong response to the vertical edge. This means that there's a strong response to this blob. This means that there's a weak response to the vertical edge. And then they're mixed up. So it's a mix and match. So the question is, which image corresponds to number 1? B, right, because I've got these vertical edges. This one has a lot of vertical edges. So that's a match. Which one responds to number 2? C, right, because I've got, this has a strongest response on these diagonal edges. These edges are diagonal. That corresponds to C. And then the remaining is A, so note that this has like lily pads or mitochondria, I don't know what it is, some blobs. And so you get a bunch of blobs here, strongly responds to the blob filter. So it's just to show that, that with this simple technique of creating a bunch of filters and then looking at the magnitude of the responses of those filters, you can get a characterization of the texture that can be used to classify a texture or otherwise represent it. Question?
Why is B responding to the blob?
So the question is, why does B respond to this blob filter as well? If you look at it, so it's kind of hard to answer generally, but if you look at some areas, there's places where there's a dark here surrounded by bright, for example, or where you've got like a little bright spot that's surrounded by dark. So even though we don't think of it as being a very blobby texture, there's a lot of local areas where it satisfies the criteria of that filter. It's more blobby. I guess another way to think of it, we would probably describe it as knobby rather than blobby, but it's more blobby than, say, if we just had a striped shirt. That would probably have a relatively weak response to this. Although even a striped shirt would give like a non-zero response, because at least you'd have white over here versus dark in the middle. So there's the match. There's another way that you could represent the texture would be to take at every pixel, you store all the responses at that pixel of all the filters. So if you have 16 filters in your bank, you have a 16-dimensional representation at each pixel. And then you can compute a histogram, which means like a count of how many times you see some vectors that are similar to some prototype. So computing histograms as feature representations is something that we'll talk about later in the class. So I won't, in this semester, so I won't talk more about it now. All right, so I also want to talk about compression a bit. So you probably, again, this is something that you may or may not have really put much thought into, but it's pretty amazing that you can take a 4-megapixel image that has 12,000 kilobytes, and you can compress it into a 400 kilobyte image without really noticing any change. Maybe you can even do it losslessly. So that's a huge compression. So images are really highly compressible. So what is it about images that makes them so compressible? Right, they're largely smooth and largely low frequencies. And so all the compression methods basically take advantage of the fact that a pixel looks like its neighbors. Or another way to view it is that it's once you subtract the mean, most of the values are small. And then there's, So here's how JPEG compression works. So I think this is kind of interesting because everyone uses JPEG compression, but most people don't really know how it works. So here's a classic image, the Lena image. So first you extract different patches, 8 by 8 blocks from the image, and then each block is separately compressed. The first step is that you apply what's called this DCT, discrete cosine transform. It's just basically you take the dot product of each of these patches, each of these filter patches with the patch here. So this will record the average value. This will record kind of like the vertical, large-scale vertical edginess. This records the super high frequencies. And this set of little templates or filters is created in a way that they're a basis function, meaning that if you get the response of an image patch for each of those, then you can reconstruct the original image patch from those responses. So if you just take you create responses by multiplying each of these blocks with, say, this block, then if you take those responses and multiply them back by these templates and add up all those resulting values, then you'll get back the original patch. So what it's doing is basically decomposing that little patch into different frequencies. So here, this is the DC frequency, or the average intensity. And then as you go down to the bottom right, you get into higher and higher frequencies. And then we've compressed those responses. So there's a couple ways that the compression is done. The main thing is that you quantize. So you say that instead of representing this number as negative 415.38, you have some quantization table that says that I only care how many times 16 can go into this number. So 16 times negative 26 is, I don't remember what it is, but it's approximately negative 415.38. Then when you want to reconstitute the original value, you do negative 26 times 16, which will give you back something that was close to the original value. So this is lossy compression. If you have a quantization table where these values are greater than 1, then it's lossy. And notice two things. So one is that you've got typically lower quantized values in the upper left side of the pyramid, of this table, I mean. And also, so here you're doing some pretty heavy compression on the high frequencies. Also, the values tend to be much higher in the upper left side than down here. So what ends up happening is that after you quantize means that you take a continuous value and then map it onto an integer. After you quantize, you get a whole bunch of zeros in the bottom right side of the triangle. And that means that you've got something really easy to compress. So you can do the quantization and then zip this thing. And then to recreate the original image, you unzip, multiply these values by these values, and then you get your filter responses, multiply those responses by the filters, and you get back your uncompressed image patches. So here's the JPEG compression summary. You first convert an image to YCRCB. That's one of the representations we talked about. This is a linear transformation, so it's really fast to compute. And then you're basically decomposing the image into the intensity image and the two chrominance images. You subsample the chrominance images by a factor of 2. One reason to do that is that color is interpolated anyway. If you remember, when you capture an image, it's with a Bayer grid where you're only capturing red or green or blue at each pixel. And then you fill in the missing values with some interpolation. And so really, the resolution of the color is not as high as every pixel. The other thing is that people's resolution for color is pretty bad for the same reason, because people basically have a kind of like Bayer grid as well, where our cones are detecting red or green or blue. Then we split the image, split each of the images into blocks. We can then process like each channel separately. Typically, you split them into 8 by 8 blocks, and you subtract 128. That's just so that the DC values will be closer to 0 as well, assuming that the average intensity of the image will be about 128. This is in UN8 form. Then for each block, you compute the DCT coefficients. Then you coarsely quantize. So many high-frequency components will be 0. And then you encode, for example, with Huffman coding. So it's a pretty simple method. And if you compress really heavily, then it's going to distort the higher frequencies that are in the image. And so you'll notice artifacts from that. Also, if you compress very heavily, you notice that the image looks kind of blocky. And that's because the compression is done on these separate 8 by 8 blocks independently. Another form of compression that's common is PNG. PNG is really simple. So it just says for every row, you have a rule. So the rule could be that I say that X is the average of A, C, B, D, or X is equal to A, or X is equal to the average of A and B. There's just a few possible rules. you choose a rule for each row, you predict the pixel value based on that rule, and then you store the difference. So if you had a completely smooth image, then you'd always be able to predict a pixel's value based on its upper left neighborhood exactly. So you'd get like zeros everywhere except for the upper left pixel. So then it's very compressible. So you just store the difference of the predicted and actual value, and then you pk-zip it, which is called the deflate algorithm. And then it's lossless because you're storing the difference between what was predicted and what was actual. So then you, again, like predict based on the upper left. You start in the upper left corner of the image. You use the rule that you created to predict a pixel's value based on the uncompressed value so far. Then you add it to the difference, and then you keep on doing that going in scanline order. So the last application that I want to talk about is denoising. So denoising is the process of trying to remove variations of intensity that are due to having limited light or not having enough light to get an accurate measurement of the average intensity. So here's a noisy image. It's like all speckled. Simple denoising method is that we apply a Gaussian filter. Because the noise is all high frequency, it gets rid of the high frequencies it gets rid of the noise. But as you filter with bigger and bigger Gaussians, or Gaussians with bigger and bigger standard deviations, you more aggressively filter out the noise, but then you also filter out the high frequencies that are there in the original image. And if you have, there's some kind of noise called salt and pepper noise, which is when, like, rather than it being slight variations of the true values, you have like some missing pixels or some places where the pixels are severely distorted. When you smooth with a Gaussian filter, you sort of spread that distortion across the local neighborhood, so you get a bad result. So another technique that's often used is something called a median filter. So for median filtering, you operate over local windows, and you replace the center value with the median of that window. So this is obviously not a linear filter, but it's still possible to do it pretty efficiently. There's O of 1 algorithms per window. And the advantage is that you get more robustness compared to Gaussian. So if this is your input, then if you do a Gaussian filter or a mean filter, then this little outlier will kind of distort the whole local neighborhood. And also, when you smooth over the sharp boundary, you get like a smoothed response over the boundary. If you have a median filter, this is in one dimension, then you get rid of the outliers without distorting the local neighborhood, and you also keep the sharp boundaries. And that's just because you're picking the value that's most represented in the local neighborhood instead of averaging them. So if we look at that on some images, if we've got this terrible noise here, which could be like from a scanner that has dust on it, for example, then if you do median filtering, it gets rid of all of that noise while keeping the boundaries that are in the original image. So median filtering is called an edge-preserving filter. It preserves edges, gets rid of outliers, and it still gets rid of noise. So Gaussian will tend to be a better filter if you have white noise, because it's the correct model for white noise. Median is for other outliers or other kinds of noise. So just one more minute. So just to briefly mention some other nonlinear filters. So you can also do weighted median, where you do the median, but you weight values that are further away from the center pixel less. You can do a clip mean, where you take the average, but you ignore the outliers. And then bilateral filtering, where you average the values, but you weight them by both the distance to the center and by the similarity of color to the center. So bilateral filtering is another more complicated kind of edge-preserving filter, but it's a good filter for like graphics usage. So in summary, we talked about several applications of filters: template matching, where you can use SSD or normalized cross-correlation; Gaussian pyramids for coarse-defined search and multi-scale detection; Laplacian pyramids, which provide a more compact image representation and can be used for compositing and graphics; compression; filter banks for texture, and denoising. And in the next class, we'll talk about edge detection. Thanks.